Next, we'll look at nested quantifiers, where in a statement you encounter more than one quantifier. They might be the same type, like both for all quantifiers or both that exist quantifiers, or they might have different types. Let's see a couple of examples which will make it more clear. For instance, you have the commutative law for addition here. If you remember, the commutative law says if you switch the order of the operands, the result will not change. Essentially, that's it. So we can express this in first order logic as for all x, for all y, x plus y equals y plus x. Okay, that's the statement of commutative law. Here, since we have two variables, of course, we need to have two quantifiers, and we have to state this rule in in the most general sense using universal quantifiers. Sometimes you can see this expressed as for all x, y, okay? X plus y equals y plus x. Now, this tells you that there are actually two quantifiers since you have two variables, but they are of the same type, so I combine them into a single quantifier. Now, this makes for easy reading and notation, um, smaller notation, let's say. However, in order to be rigorous, we are not going to usually prefer this, okay? In our discussions, we are going to usually prefer stating the quantifiers explicitly. The next example is distribution law, again, of multiplication over addition. So here we have actually three variables for all x, for all y, for all z. X times y plus z equals x times y plus x times z. Okay, so this is how you state distribution law in first order logic. Another example in which you have actually different types of quantifiers now is existence of additive inverse. Additive inverse, if you remember, is for a number, the number for which the sum makes zero. Okay, for instance, the additive inverse of 5 is -5. The additive inverse of -4 is 4. So the statement here is for all x, there exists a y. Okay, so for all possible values of a number, let's say, and we are not explicitly stating it, but we can assume the domain is real numbers. For all x, there exists a y such that x plus y makes 0. Okay, so this talks about the existence of additive inverse for all numbers. Okay, now one important aspect when you have multiple quantifiers is the order. Okay, because if you have the same type of quantifiers, like the first two examples here, the order doesn't really matter. For instance, this one I can write also as for all y, for all x, x plus y equals y plus x. Doesn't make a change. Okay, it's the exact same statement. It means the same thing. However, like this one, if you have different types of quantifiers in your statement, the order is significant. Okay, when you have different types of quantifiers together, the order is important. Take this one for instance. Again, this one, copy it here. For all x, there exists a y such that x plus y equals 0. What it says is for all numbers, there exists an additive inverse. If you switch to quantifiers and write there exists a y for all x, x plus y equals 0. Now think about this for a minute. There exists a y, so there is a y, just there exists a y such that for all x. Now for all x comes after. That is significant because this now binds all numbers to the same y. Okay, so for there exists a y value for every x, for every value, every x value, when you sum them up, you get 0. So what this says is there exists a number which is the additive inverse of all numbers, which is clearly false, right? Well, additive inverse exist, but they are all different for different numbers. That's not what we were trying to say. So this is true, the first one, but this one is not true. It's false because it actually says something different. Okay, so next we'll look at how to negate quantified statements. And essentially, this also summarizes the relationship between the two foremost quantifiers for all and exists. Now, consider the meaning of this statement. For all x, p of x. This means p of x holds for every possible x. If you negate this, okay, so this is the notation, what you are saying is p of x doesn't hold for every x, okay? Now, you have to be careful here. We are not saying that p of x holds for no x value. That's not the negation, okay? The original statement is p of x holds for every x, so its negation is doesn't hold for every x. So what we are saying is it might not hold for some x values, maybe not all of them, but some of them makes p of x false. Okay, p of x may not hold for some x. This means there are some x for which p of x doesn't hold. Now we are talking about the existence. If you are careful, like so there exists x value one or more, we don't know, but there is at least one for which p of x is not true. Okay, so the negation of this statement is this. Okay, so simply not for all x. P of x is equivalent to there exists an x, not p of x. Okay, so this is how you actually um, uh, move the negation inside a universally quantified statement. And also, it's quite similar the other way around. If you have an existentially quantified statement that exists an x, p of x, this means that p of x holds for at least one x. If you negate this statement, it says that p of x doesn't hold for any x. Okay, there doesn't exist an x for which p of x is true, which means for all x is false. So for all x, not p of x. Simple as that. Okay. So these two are De Morgan's laws in first order logic. Okay, so not for all x, p of x is equivalent to there exists an x, not p of x. So you change from for all to exists and put the negation inside. And similarly here, not there exists a p of x, that's equivalent to for all x, not p of x. Again, if you have a negation in front of an existential quantifier, you switch it to universal quantifier and put the negation inside.